This server represents the volume product, I think, for Intel Xeon. We're talking about scale out. This is a typical server like you would buy for a virtualization farm or really any kind of tasks that you're going to run in a data center. You could buy a rack of them. You could buy a single individual machine. We're going to take a look at this configuration because it's 136 PCIe Gen 5 lanes, but it's only a single socket. You can put up to 4 terabytes of memory in this chassis. As configured, I've got 8 NVMe at the front. Most of the PCIe lanes are routed to the back, but this chassis is available in a whole bunch of different configurations. We're going to benchmark it. We're going to take a look at the layout. We're going to take a look at some clever stuff in the design from Supermicro and our SYS-212H-TN. Let's take a closer look. So Xeon 6 is a little bit of an unsung hero. It's the best Xeon that Intel has done in literally 10 years. Not even kidding. The CPU that's in here is one of their flagship CPUs. It's 80 cores, 160 threads. It's a single CPU. But even though it's a single socket, it's still 136 PCIe Gen 5 lanes. There's a few more lanes there? PCIe Gen 5? Yeah, there is. Let's take a look on the inside. A lot of people don't realize how much heat the DDR5 can generate. It can generate quite a lot of heat. Now, this is an 8 memory channel platform, and we can see that our motherboard layout here supports 2 DIMMs per channel. There's a bunch of different memory configurations that are available in this chassis, and there's a bunch of different memory configurations depending on what you want to do. If you want MR DIMMs, that will be good for up to DDR5 8800, but right now, MR DIMMs capacity-wise, you're going to be limited to about 512 gigabytes. If you're willing to run 2 DIMMs per channel, it's DDR5 5200, you can do 4 terabytes in this platform. Otherwise, 2 terabytes, DDR5 6400. And that's kind of the sweet spot of capacity and memory bandwidth. Even though this is a single socket, when you think about virtual machine hosts, you think dual socket configurations, usually. But when we're talking about 40, 60, 80 cores per socket, a lot of organizations aren't really comfortable with the blast radius, as it's called. So if you lose a single machine, how many VMs were really running on this? Because the typical size of a VM is 12 to 24 cores per virtual machine. And so a single socket can make a lot of sense for all of these scale out things that an enterprise is going to do in this configuration, but you don't sacrifice anything in terms of PCIe lanes or connectivity or anything else. This is a sort of do pretty much anything you want chassis. Now in our configuration, I've got 8 PCIe Gen 5 NVMe at the front of this, and all of them have 4 lanes. So we've got a total of 32 PCI Express lanes at the front here. 4/8 is 32. That's how you do that. This chassis can be configured with up to 24 NVMe at the front, but most of the PCIe is routed to the rear. And how they do that, modern server design, is the use of MCIO connectors. MCIO connectors are fantastic. They've shown up on workstations. They've shown up on AMD servers. They're on Intel servers, single socket, dual socket. The most wildly expensive servers, the most affordable servers. MCIO connectors let you choose how you want to allocate your PCIe lanes. And this is a fantastic thing in terms of server design. And that's how Supermicro is able to be so flexible with this chassis. When we're talking about MCIO connectors, you can see here that they're scattered all around the board. Some of them are routed to the front for your NVMe. Some of them are routed to the rear for your expansion slots. And your MCIO connectors can have 8 lanes. If you want to have 16 lanes split into 2 X8 PCIe slots, not a problem. You can configure that, and the platform can configure that, and then the 16 lanes will split into 2 X8 lanes. As we've got this thing configured, because we've allocated most of our PCIe lanes to the rear instead of the front, we've got 5 Gen 5 PCIe X16 slots, plus an X16 AIOM, which is an OCP3 compatible slot, just right on top of my existing OCP3 AIOM module. So there's actually 2 modules at the rear here with up to 16 lanes of PCIe Gen 5 each. So right now I'm running a dual 25 gig NIC, but I could have 2 25 gig NICs for a total of 4 25 gig ports, or even the 100 gig NICs from Intel. I've got an E810 around here somewhere. We could just throw that in and be able to do that. I've also got some ConnectX 6 cards, 16 lanes, a A lot of PCIe connectivity there, so we'll throw that in and see how that works. If you're doing virtualization, especially desktop virtualization, this configuration is nice because you can run a lot of network connectivity, but you can also add GPUs for virtual desktop acceleration, and you still got a ton of local connectivity. You could run, your network connection with a SAN type connection. You could do a hyperconverged, so you've got lots of local storage. When you got 8 NVMe bays, that's pretty significant. I mean, even for a VDI type scenario, 8 NVMe bays is going to give you plenty of capacity because 16 and 32 terabytes are the sweet spot for NVMe. And so you'll be able to put that at the front and run this configuration and do whatever you need to as far as VDI. And, I figure you've got, 3, 4, 6 chassis when you're building a cluster like that. If you're doing other types of PCIe connectivity, PCIe accelerators, FPGA cards, custom things like that, there's a lot of PCIe connectivity routed to the rear of this chassis in this configuration. If you'd rather have 16 NVMe and less PCIe at the front, it doesn't really change the core of the system. It just changes how the MCIO connectors are routed. And so there's different modules from Supermicro. These are all assembled here in the United States. So you just call them up and you say, this is the configuration that we're looking for. How do we achieve this in terms of PCIe connectivity for the rear, for peripherals, and PCIe connectivity for our front IO? And Supermicro will help you configure a chassis that makes sense to be able to do that. If you've been working on servers for a long time, the MCIO connectors might look a little foreign or be a little bit more of a departure for you. You may be used to riser cards plugging into printed circuit boards. That is kind of a monolithic design. That can still make sense in some scenarios, but the MCIO connectors here give you maximum flexibility for connecting whatever sorts of PCI Express peripherals you need. And basically everything is a PCI Express lane at this point. Gone are the days of specialization. You can still run legacy SAS and SATA drives on your front panel connection here on the PCB, the backplane for your NVMe. There are 2 4-lane connectors for connection to a SAS card. So if you want to add a PCI Express serial attached SCSI add-in card and run some legacy SAS in the front, you still can do that. But my recommendation is NVMe. In this day and age, NVMe. When you have a processor like this, NVMe. The other thing with Xeon 6 that I will go off roadmap, off script here for a second, this is an 80-core CPU. It's expensive. Xeon 6 has some other options that you shouldn't sleep on if you're looking for something that's scale out, but something more in the 24 to 32 to 48 core variety. There are a lot of really good options in the Xeon 6 family. Take, for example, the Xeon 6521P. If you get this as a bare bones chassis and you outfit it with a 6521P, that's sort of the entry level, starter CPU that I would go with if you were going to do a platform like this. The 6521P is pretty easy to find street price for just about $1,000. It's 24 cores. It'll clock up to 4.1 gigahertz on all 24 cores, which is fantastic. And it's just about $1,000, but it still gives you all 136 PCIe lanes. So if 24 cores will do the workload that you're interested in and you need a ridiculous amount of PCIe connectivity, that will do it. That will do it on this platform. That would make sense, I think, maybe to deploy to 16 NVMe and then some high speed 200 or 400 gigabit NICs so that you're basically putting NVMe on the fabric, but you still have a little bit of CPU capacity to run a few small virtual machines. When you're moving that much IO, especially with PCIe Gen 5 IO, it does consume a lot of CPU horsepower, so more cores might make more sense. In this configuration, because I've got 80 cores, this can pack in a fair density as far as virtual machines go, but I still have a ton of local storage, a ton of PCIe connectivity for local storage, and I still have a ton of PCIe connectivity off the system. As far as AI workloads go, well, look, you've got 4 double height PCIe slots in this. You could put 4 H100s, 4 L40S in this platform. You have plenty of cooling in order to be able to do that. And our power supplies. Our power supplies are 2 kilowatts, so you'll be able to handle 4 300-watt GPUs plus the power for the rest of the system, no problem. And remember, if you are going to pack in, 2 or 4 terabytes of memory in this platform, DDR5 uses a non-trivial amount of memory. You got to figure that in your memory calculations. Just 3 or 4 generations ago, it's like, we don't really need to figure the memory calculation when we're just, doing the back of the envelope power estimation and power calculation, but you do on this. Now, because this has an out-of-band management controller, it's the ASP2600, it has its own dedicated NIC. This platform lets you move that and share that on the AIOM module, but you have to get an AIOM module that supports that. The ones bundled from Supermicro will, of course, do that, so I can do out-of-band management through my fiber optic connections here at the rear. But depending on the NIC that you add, if you're going to add an aftermarket NIC, that's a consideration. That's a new standard that you should look into. I like the out-of-band, the dedicated port for the out-of-band management for this. It does not have any other built-in networking. You really need to be using an AIOM module. But you can use an AIOM module with up to 16 lanes of PCIe Gen 5, so 200 gigabit, 400 gigabit, entirely possible in this platform. I'll also point out on the motherboard, we have 2 unused M.2 ports. If you prefer using M.2 for your boot operating system, you can totally do that and then not use your front NVMe. There's also an unused PCI Express 5 gigabit header. So you can have 2 internal USB 5 gigabit headers if you prefer to do it that way. Although mostly people don't run the boot operating system or anything like that from USB. I see more network boot for the operating system these days than I do USB. Actually, it's been that way for a few years. But boot NVMe, some people prefer to put the operating system on the internal NVMe. And so you can set up a RAID 1 with the internal NVMe, and that works fine. In terms of GPU power from your power supplies, that's all routed through the motherboard, through these headers on the motherboard. Depending on the configuration you order, Supermicro will supply the cables for the GPUs that you're using so that they'll be powered appropriately. One of our headers at the front supplies power for our NVMe bays. There's an extra unused port there. And then there's another 6 scattered around the rest of the board. Again, having headers gives you options for where you want to route things in terms of chassis design and makes this design eminently reusable no matter what sort of configuration you need for your particular application. And look at the internal configuration. There's so much room for activities. Plenty of room here. It's nice to see that because everything has been turned up to 11 in terms of density with the water cooling and the giant copper plates and everything else like this. This is simple, tried and true design. And this is, again, a volume product. This is the thing that everyone is going to buy. So that's enough of a chassis tour. Let's get this thing put back together and then put in the rack, and let's run some benchmarks. Okay, benchmarking. What's the benchmarking result? This CPU is positioned interestingly, I think. So this is a 350 watt TDP CPU, reminder. And AMD has their 400 to 500 watt CPUs in the 12 memory channel socket. And then they also have AMD EPYC Sienna, which is really built for embedded systems. And that's Zen 4, but that's a 6 memory channel platform. Things like the 45 drive Stornado and other embedded systems, like that makes sense. And that's a long-term support socket. Like that's going to be around for 5+ years because that's what a lot of customers want. There's not a lot of inertia for changing things every year, every 18 months in that scenario. And in a lot of ways, this CPU from Intel is the same way. It's not the most fire-breathing thing you can get with 8 memory channels, but Intel thinks 8 memory channels is a better bet for longevity than 6 memory channels. And the benchmarks kind of back up Intel's positioning here. This CPU is well positioned in terms of performance. So if you look at timed compilation like FFmpeg or Godot, it lines up pretty well between that 6 memory channel and the 12 memory channel thing. I mean, the 9575F is a fire-breathing 5 gigahertz 64-core CPU. This thing is 80 cores, but it is much more conservative on power. So each individual core is going to use less power, and the turbo values for those, single core clock speed on that CPU is not going to be nearly as high as 5 gigahertz. Uses less power, runs slower. There's nothing wrong with that. That's good for certain workloads. And it does really well with the timed compilation. Keep in mind the 8534 is also a 64-core part, with the 8534 at 230 watts in this configuration. So it's like 230 watts and then 350 watts and then 450, 500 watts on the 9575F. So it's a little bit of a gradient here. But again, Intel's targeting that 350 watt TDP socket configuration. If you're looking at a build server, the Ninja results here are great. OpenSSL, so like web server, key signing, encrypted traffic where you're relying on the CPU. And this is even before we get into accelerators that Intel has. Intel has on-chip accelerators that can accelerate certain cryptographic workloads where it will do even better. But it's holding its own even against the 9575F because of architectural choices that Intel has made. Now, it's not all roses for Intel in some of the other algorithms like SHA-512, then yeah, the 9575F is going to take the crown here. But it's doing substantially better versus the 8534P. This is also because generally Xeon 6 is toe-to-toe or better than Zen 4, but it has trouble keeping up with Zen 5 when everything else is alike. We did our benchmarks on the Intel 6980P. It is Xeon 6, the 12 memory channel configuration, easily the best Xeon that Intel has done in 10 years, and they had performance leadership versus Zen 4. Zen 5, a little different story. The Zen 5 came out like a month after the 6980P, so... But for this CPU, it's about bang for buck and about performance per watt per dollar, something like that. And for like AES-128 GCM, Intel holds its own here. It's meeting the performance of the 9575F. Even AES-256, the 9575F pulls a little ahead here, but keep in mind the Intel's using significantly less power. SpeedDB, random read while writing, Intel's holding its own here. Again, it's doing pretty well against the 9575F in a lower power envelope, and doing significantly better than the even lower power envelope AMD EPYC Sienna. Some of these benchmarks are also memory bandwidth benchmarks, but I like to show this because sometimes the 8 memory channel part from Intel can outperform the 12 memory channel part from AMD. I thought the result for Google SynthMark and the algebraic multi-grid benchmark was also interesting in that Intel is doing so well here, but it falls a little behind on CoreMark, maybe a little bit more behind than I would have expected based on the performance elsewhere, and this is no doubt due to the single core clock speed. Intel's doing really well here on Lulish, but on Mini Bude, it's really not doing quite as well. It's just a hair faster than that AMD EPYC Sienna part. For the Rhodopsin simulator, 80 cores is better than 64 cores. That's why this is winning here. It's just more cores. This is an algorithm that scales really well across a ton of cores. Zen 5C would probably clean up the charts here. But again, the single socket targeting the 350 watt-ish segment. It's an interesting segment that Intel's targeting here with this TDP and 136 PCIe lanes. A lot of our other benchmarks is a similar breakdown. Depending on what the workload is and what optimizations there are, the Intel CPU does really well considering the power envelope and considering 8 memory channels. Xeon 6 is no slouch. It is a solid CPU for a lot of these workloads. NAMD and GROMAX, of course, Intel's doing very well. QuantLib, if you look at just single thread, it doesn't look like Intel's doing quite as well, but then you look at the multi-thread configuration and it's like, 80 cores versus 64 cores. They sort of make it up there. It's sort of the shoe on the other foot. I mean, historically, in the Zen 2 and Zen 3 days, that was AMD. AMD is like, well, we're not taking the crown on single core speed, but we can make it up for cores, and that's what Intel is doing here with this particular Xeon 6 part. And you can see that in the NAS parallel benchmarks as well. This is one area where Intel's software has a lot of optimizations. And also, this is significant performance uplift when we're talking about GROMAX and NAS and a couple of these other benchmarks. This is significant performance uplift since Xeon 6 launched. I mean, the cores themselves are not a lot different from when the 6980P launched. This CPU just launched a few months ago, but Intel's software team has been churning out updates, and those software updates from literally just the last couple of weeks make significant differences in these benchmarks. And AMD also benefits from those changes. Of course, OpenFOAM and OpenRadios scale really well and are optimized for the Intel platform, so they're doing really well in that benchmark. Blender is more generic. Blender is hyper-optimized for basically everything, and Blender gives you sort of a raw breakdown of true performance. Similar story for LuxCore Render. OSP Ray, Intel takes the lead by a very narrow margin here, but again, lower power. The Embry result is pretty strong for Intel here. Open image denoise, of course, because Intel's got a lot of their own optimizations in their image denoiser. OpenVKL and even 7-zip. 7-zip was a little surprising here given the memory channel advantage of the 9575F. It's a good showing from Intel. And this is also has to do with the optimizations, like the low-level system library optimizations from Intel the last few weeks. Python, used for everything from machine learning to PhD research to everything, it stacks up about how you'd expect. It's a good result for Intel for Python. Of course, the 9575F takes the crown, 64 cores, 5 gigahertz. It's hard to beat that. But the 6781P showing here is quite good. OpenVINO is an interesting one because depending on what you're doing, the 9575F is unstoppable with its full speed AVX 512 and that sort of thing. But Intel has some tricks up their sleeve, like the optimized FP16 to int8 routine. It just depends on what you want to show. If you want to show FP16 to int8, Intel's ahead by a mile, even versus the 9575F. But, if it's face detection for FP16 and int8, then the 6781P is really not tremendously faster than the 9575F. And this is a big reversal because when the 6980p launched, OpenVINO on Zen 5 in a lot of scenarios was faster on Zen 5 than Xeon 6. But here we are 8 months later, and Intel's got the optimizations for OpenVINO in. So what's the bottom line with the performance here? The performance is very impressive. Intel Xeon 6 remains the best Xeon that Intel has done in years, but the competition from AMD is fierce. And depending on what your workload is and what you're doing, you have to look at it. This platform is unique in that it's got a pretty good power target. I mean, Intel historically is not known for having a very power efficient platform, but this shows that they're taking that seriously, which is amazing. For some of these workloads, this is an amazing point on the curve in terms of balancing performance, power, and platform features, 136 PCIe lanes plus memory. It's definitely worth considering this platform, but you also have to consider in the larger spectrum of everything what your workload is, what sort of performance you're looking for, and what specifically you are doing with your server. This is a good all-rounder. This would make an excellent platform for a hyper-converged virtualization platform because you get that 80 cores of core density, VMware platform migration from VMware to something else, platform fully qualified for Windows Server, and 80 cores. You could have two groups of, it's 40 cores. Let's see, 40 cores, more than 64. The whole hyper-threading thing probably just run with hyper-thread disabled in the Windows case so that you get two 40-core processor groups that you're working with, even though it's a single socket to make Windows happy, and 8 memory channels. The memory bandwidth is good for that. As a storage platform where you've got a ton of high-speed, PCIe Gen 5 devices connected, this would also make a particularly good choice. Intel has some other high clock speed Xeon CPUs that would be good maybe for a storage platform, because depending on what you're doing for your storage platform, higher clocks is better than more cores. But Intel has some options for that in the 350 watt power envelope. And overall, Intel is looking at a little bit of a gap here in AMD's lineup, in my opinion, because you've got the 12 memory channel, and yeah, you can run a 12 memory channel CPU with 8 memory channels. There are AMD motherboards that are designed for the 9000 series EPYC that only physically have 8 memory channels, even though the processor supports 12 memory channels. And that is certainly a thing that you can do, running 24, 48, 64 cores on that platform, and then can you get the performance out of it when it's running in 8 memory channel mode instead of 12 memory channel mode? But this is designed for 8 memory channels, and Intel is certainly maximizing the benefit that they get from the memory bandwidth based on the benchmarks. It's a very impressive result and very impressive software engineering result. So Intel is definitely in scrappy underdog mode, but this is a significant upgrade over 5th generation Xeon. The bottom line is that this is a genuinely good CPU for workloads today in 2025 for the things that you want to be able to run and that sort of thing. I think the future is like what's coming for Xeon 7, what's coming for Xeon 8. I think that it will tremendously bolster customer confidence seeing this kind of update and this kind of commitment on Intel processors into Xeon 7 and Xeon 8. So here's hoping for the future. But for Xeon 6, for this platform, for a single socket, this is pretty impressive. It's not the 6980p, it's not the top flagship CPU, but it is something that is impressive for the point that it's at in the market. So maybe worth a look. I want to list level 1. If you have any questions or you want to see a test workload or something, hit me up in the forum. All right, I'm signing out and I'll see you there.